interesting. All right, we're going to be looking at Chapter 9 today, a couple of important points. But before we do that, I just want to mention one thing we did look at in Chapter 8. We used our equations to make predictions. Just to remind you, we were given a specific value for the x variable, and we simply plugged that in the equation to make a prediction. So I mentioned that because that's one topic that shows up again in Chapter 9. But here we define a new word, extrapolation. That's when we make predictions outside kind of the range of the data values we've already collected. So to illustrate, here's our equation. Again, we're used to seeing this. The predicted cost for a property monopoly, 67.28 plus 6.78 times the number of spaces from Go. And if I want to predict the cost of a property that's 63 spaces from Go, I would simply plug that into my equation. Okay, we've seen that before. Again, I'm plugging in 63 in the spot where the number of spaces goes. And after I put that in my calculator, I get that the predicted cost is $495.68. However, something we need to watch out for. If we look back to our original set of data, okay, it's kind of got some marks on it, but you'll see we started gathering data at one space from Go, and then we went all the way, they're in order, to 39 spaces from Go, right here, 39. So making a prediction anywhere between 1 and 39 spaces from Go makes sense. However, anytime we go below 1, so if I was making a prediction about 0 spaces from Go, or, gosh, negative 12 spaces from Go, that's extrapolation. It doesn't make sense. And certainly if I go past 39, so I wrote down 42, or the one we just did was 63, that's extrapolation. It's dangerous because we do not know if our pattern continues. See if I can pull back up our original scatter plot for this set of data. Here we go. We had this nice linear trend, but when we extrapolate, we're saying something about way out here a data point. I don't know. Maybe once I get here, the trend changes. Maybe it flatlines. Maybe it goes down. I don't know. So it's not fair to make predictions way out here. Let's go back to our page for today. So again, extrapolation is bad. I don't know whether or not this number really makes sense because I don't know if my trend continues. So that's just one thing you're going to see in Chapter 9. Another thing that you're going to read about in Chapter 9 are what I call a collection of weird points. Your book actually defines some different names, so you should look these up: leverage points, outliers, and influential points. I'm not really worried about distinguishing between these three. What I want you to be able to just identify is why a point is weird. I will specifically point out what an influential point is. These ones are important. Put a star by it. Because these are points that change the slope of my least squares regression line. And since that's really what we've been focusing on is this line, and specifically we'll see all the way in Chapter 27 why the slope is so important. But anything that changes the slope is of most interest to us. So to just kind of help us imagine weird points, pretend that I've gathered some data about height and weight for our class. I didn't actually gather this data, we're just imagining. And this scatter plot is not unrealistic. Height and weight generally make a nice positive linear trend in a scatter plot. As you might imagine, the taller you are, the more you weigh, just in general. So let's think about what if we added some perhaps weird points. So the first one I'm going to consider is Shaquille O'Neal. Sorry for the slightly outdated basketball reference. He's very interesting because Shaquille O'Neal is very tall, and then as you might expect, because he is tall, he weighs more. So if I was to graph him with our students here, the point might be something like that, okay? Notice Shaquille O'Neal, if we considered only his height, we would definitely call him an outlier. nobody is close to 7'1" in our class. But when we put both height and weight together, sure seems like he follows that same trend as the rest of our class. So certainly unusual, but follows the trend, so not quite as interesting. All right, what if we added a sumo wrestler? Picture a sumo wrestler in your mind. Okay, they're not particularly tall, but they weigh a lot. So I might put the height somewhere here, average for our class, and then, give myself plenty of space. It's going to weigh a lot. So without the green point, we had kind of this general trend. And when I consider the green point, it might pull my line up a little bit towards him, okay, pulling up, but it's not really going to change the slope of my line. Certainly that point is unusual, but it's not really changing the slope. So not most important kind of point for us. All right, so what is a point that's going to change our slope? We call those influential points, and Manute Bol is a great example. Manute Bol died in 2010. I looked that up. Famous basketball player because he was very, very tall. Look at that, 7'6" and very thin, 200 pounds. Just because I know you're curious, I did include some pictures. All right, so a couple pictures of Manute Bol. All right, just for some reference, you can kind of get that in your mind of just how tall and skinny we're talking about. So if we add Manute Bol, if you were to, come back from the grave and visit our classroom, and we were to put him on our graph, well, geez, 7'6", I'm, way out here, even farther than Shaquille O'Neal was, but only 200 pounds. I mean, I'm, maybe in here somewhere, okay? So what's going to happen is this point that's not following my trend is going to pull the slope of the line down towards it. So I'm going to end up with a new line that's probably something a little bit more like this. It's pulled my slope down, so this point right here, Manute Bol, is influential. Without him, I have a different slope, a different line. So again, just some examples of some weird points and kind of how they can affect our lines. The last thing I want to mention about Chapter 9 is a very common mistake. So here's a little story problem. A vocabulary achievement test given to elementary school children discovered a strong association between weight and vocabulary score. So you might be asked to comment or critique a comment about something like this. So what it's really saying is there's an association between weight and the vocabulary score. Okay? And you're probably imagining it's going like that. And oftentimes students say, well, of course, there's a relationship between weight and vocabulary score. That makes perfect sense. So does that mean that if I were to go out and eat, 5 dozen Twinkies and put on 20 pounds, I'm just magically going to know more vocabulary? Well, of course not. Because remember, association or correlation is not causation, right? There's no cause and effect just because there is a relationship. Remember, storks, right? And human population, okay? Just because we see a relationship doesn't mean it's cause and effect. So that's what I wrote here. A linear relationship does not mean X causes Y. There could be what we call a lurking variable, another variable that's not on the graph that explains that relationship. In this story problem, that lurking variable is age. Think about it. In elementary school children, the older you get, the more you weigh, and the older you get, the more your vocabulary goes up in general. So age could actually be what's causing this relationship to appear. There could be something else. Age is, of course, the answer in this situation, but we just want to watch out for those lurking variables. Something that's not showing up in our data, something that's not on the graph, that could explain the relationship. Be very careful that you don't get caught in talking about X causes Y. We cannot prove that. We'll talk about how to prove that in Unit 3 when we get to experiments.